So here we have our favorite drum loop. Here we're going to do some slicing. So buff onset slice. And if we do the slicing, we can see our drum loop with some slice points. And these are going to be the slices that we are going to analyze and then plot. And if we want to see the actual slices, fluid.buff to list with the source as the slice points buffer will give us those as a list. Okay, so we're going to build a little analysis pipeline again to get out our spectral centroid, and in this case also loudness analysis for each one of these drum hits as our different slices that we'll be plotting. We can actually start with this because this will be our first step, will be to get these slice points out of our buff to list buffer. This bang will be our bang for causing the analysis to run. And just like before, I'm going to use a ZL stream 2 to get those adjacent pairs of slice positions to use as my start and end points. I'm going to, as a meta comment, go a little faster this time since we just did this, but I do want to step through it again and have us think through it and build it for those of you who are patching along. I'll use a trigger to do a bang and a ZL clear. You clear this guy. Oops, this should be a list, I mean. Clear this guy and then send the list of all the slice points into my ZL stream. And then I will put my fluid.buff spectral shape analysis here. This is going to give us a set of spectral analyses. So for our given section of the buffer that we're analyzing, we will have a spectral centroid analysis, a spectral spread analysis, a spectral skewness, kurtosis, roll-off, flatness, and crest, all analyses of the spectrum in this 7-channel buffer that fluid buff spectral shape will return to us as the analysis. Frames in this analysis buffer will be 1 frame per FFT frame in the slice that we are analyzing, and we'll get that same analysis in the channel for every FFT frame in the slice we're analyzing. Again, we're going to use the @select attribute to select a subset of these. In fact, we just want to have the centroid analysis, so that's what we'll ask it to give us. But the fluid buff spectral shape analysis can give us all of these if we want, or a subset of these if we use select. So I will say that the source should be my buffer called sound. My features, again, the word features here, meaning where the audio features that it will be analyzing for, should be written into a buffer called spec buff. And we'll say @select centroid. I'm also going to put in here again the @numchans1 to specify that we just want to be working in mono right now, because stereo makes a lot more data and can be a little bit more complicated. I said there's a buffer called spec buff, so I better make it. And then I will do the same thing I did before to say, do the bang minus to get the difference between the two values and send that in as num frames. And then also send in the start frame. And then once I am done sending in the num frames in the start frame, I send in a bang to tell the buff spectral shape to actually do the analysis. Okay. Now we'll have our just centroid value because we used @select to select just the centroid. This spec buff will be a 1-channel buffer that has all of the centroid values, 1 from each FFT frame. And what we're going to want to do is use our buff stats to get out the mean spectral centroid of this time series of spectral centroid analyses. So I'll say trigger bang here to convert this into a bang, and then I'll say fluid buff stats. The source will be my buffer spec buff, where those spectral centroids are stored. My stats will be a buffer called stats buff, I'll make in a moment. And I'll say at select mean, because that is the statistical analysis that I would like. Better make my buffer called, stats buff. And now we'll have our mean spectral centroid in this buffer called stats buff. And again, the way that we're doing that, it'll end up being just a single frame and single channel buffer that'll have that one mean statistical summary. The next thing I'm going to do is I'm going to take this mean value, I'm going to copy it into another buffer. And this buffer is going to be a buffer I'm going to call point. And what I'm going to do is I'm going to build my data point in this buffer. So for each one of these sound slices, I'm going to have a spectral centroid analysis. I should say a mean spectral centroid value. And I'm also going to have a mean loudness value. And these two values, mean centroid and mean loudness, that's going to be my data point to represent this particular sound slice. Because I know that this point is always going to have two values, I'm going to say at stamps 2, because I just know right off the bat it will always be that. This could actually change if I used a buffer operation that would change that, but here it's kind of verbose. It's kind of being really explicit, mostly for me to know that I should have two values in that buffer, and if I have a different number than that, then something has gone wrong. In order to get my mean centroid value out of stats buff into point, I'm going to use the fluid.buffCompose object. And buffCompose is essentially a buffer copy operation. So I need to specify a source where I'm copying from. That's going to be stats buff. I need to specify a destination where I'm copying into. That's going to be point. And then there's a few other things I could specify here, like what frame to start at, what channel to start at, how many frames to copy, how many channels to copy. In this case, because stats buff is one frame and one channel, it will copy everything from that buffer, which is just the one value. So I can actually leave all of that as is. What I am going to specify, though, is at dest start frame, which is going to be the frame in my destination buffer that it should start writing at. The default for this is 0, but I'm going to specify 0 here because what I'm going to do is copy my mean centroid value into frame 0. And then I'm going to copy my mean loudness value into frame 1. And so what that'll do is give me those two values as my data point in my buffer called point. So here I'm just being explicit again. The mean centroid will go in 0, and then when I do this again for the mean loudness, I'll put a 1 there, and I can see clearly, what is going where. Okay. So now, if I were to plot this, or print this, I might want to do print out my point buffer, for example. Fluid.buff to list at source point, and run this analysis. We can see that, sure enough, I have what looks like a mean spectral centroid value for as many sound slices as there are in this slicer analysis. And then my second index, or I should say my first index in point, are just all zeros because I haven't put anything in there yet. But I'm successfully copying that mean centroid over into point and seeing it here printed out. So now what I'm going to do is I'm going to do my loudness analysis. I'm going to do a fluid buff loudness. I will say at select loudness. And then also for fluid buff loudness, I will say at source will be, again, my source called sound. This is the buffer I want to analyze. And I'll put an attribute here at features. And this will be the buffer that will write the loudness analysis into. So I'll make a buffer called loud buff. This all looks pretty good, although there's one more piece of information that fluid buff loudness needs, which frames to look at. And in fact, we're already computing that. So when we do that, we're just going to pass it right on to buff loudness as well, right? We just set that to buff loudness, and then when our data pipeline of analysis gets down here, fluid buff loudness will already know what frames to start at and how many frames to analyze. Cool. So now we're going to do the same thing we did before. We're going to get our statistical summary using fluid.buffstats. The buffer it should do the statistical analysis of, the source should be loud buff. The place where it should write that statistical analysis, we could make another buffer, call it stats buff 2 or something like this. We can actually just reuse this buffer, right? Because we've already copied out of stats buff the information that we care about from our spectral centroid analysis. So we could actually just reuse stats buff. Let's write into there again, and then we'll copy out of it again. So I can just say the same buffer here, stats buff. And then just like we did before, we'll say at select mean. And then we'll want to do the same thing we did here. Use a fluid buff compose to copy out of stats buff, which now contains our mean loudness analysis. We're going to write it into point, but in this case, we're going to not write it into the frame 0 of point. We're going to write it into frame 1 of point. And now we should have our compiled data point for each one of these sound slices at the end of this chain. Clear that guy. And I would say that looks pretty good. That looks like a bunch of average spectral centroid and average loudness pairs. Okay. So now that we have, using ZL stream, right, we're doing all of these analyses rapid fire, one after the other, using getting the start frame, num frames, doing all of our analysis, copying it all into point, and then as we can see, that's getting overwritten. The values in point are getting overwritten every time we get the next pair of indices and do the analysis again on the next slice. Because we have it in point, we actually want to store this somewhere instead of just posting it to the print window. We might want to store this somewhere so we can have access to all of these later. The place we're going to put all of these is in a data set. So we will say fluid.dataset. Let's call slices. We will use the message add point to add these points to the data set. Add point takes 2 arguments, as we saw before. The first one is going to be an identifier that will uniquely identify each data point in our data set. Put a $1 in there for now. We'll pass that in each time we compute the analysis for a new slice. And then the second argument of add point is going to be which buffer contains the data that we want to add to the data set with the associated identifier. And of course, we've just compiled this data into our buffer called point. So that's the one we will say it should look to. Now, in order to have all of this finish our analysis pipeline here and add these to our data set, we're going to use a counter again. We're going to bang the counter. So each time we run the analysis on the next slice, we'll get a new integer to identify the slice with. And then we will take that counter and we're just going to put it right into add point. And so our identifiers in this case will be just integer numbers, starting with 0 and then counting up. And this will be really convenient because this also means that the identifiers that we have in our data set will correspond to the order of the slices as they occur in our buffer, in our slice analysis here. So, this slice will be identifier 0. This slice will be identifier 1, identifier 2, 3, etc. And that'll be really helpful for later when we want to play back those slices or look up those slices and know something about those slices after we do some analysis with them. So we can just play them back very easily. A data set is essentially a two-dimensional spreadsheet, a two-dimensional set of data like a matrix. A buffer is also a two-dimensional set of data with a matrix. The reason that we're using a data set here is because once we have it in a data set, it actually allows us ways of interfacing with the data objects in FluCoMa. And the reason why we use a data set to do that is because what a buffer doesn't really have is the idea of an identifier. Now, a buffer has frames, right? We could call I want to have the data point at frame 25, and we could go down to frame 25 and get out the data there. But what identifiers let us do is they also let us think about it in a more flexible way. So if we were to say this is a data set here, which it will be shortly, if this is a data set, we wanted to filter this data set and say, okay, give me only the slices where the average loudness is above -40 decibels. We could filter all of this and we'd get rid of this one and we'd get rid of this one and we'd get rid of this one, right? And we'd only keep the slices where the loudness is above -40. But after we get rid of those, we would have fewer frames in our buffer, and then we would actually lose the coordination of which of these analyses correspond to which slices in our data set, or sorry, in our buffer here, in our slicer analysis. And so using a data set lets us associate these analyses with identifiers. And then even after we do all sorts of sorting, all sorts of querying, looking for slices within certain ranges of values, even after we do things where we do dimensionality reduction algorithm or clustering algorithms, those data points will always have an identifier that we can use to refer back to what slice it comes from. And so the identifier is really the powerful tool here that lets us manipulate the data in all sorts of ways and still know exactly where it came from. Whereas if we had to keep track of what index things were in a buffer, it would start to get more complicated quite quickly. The only last thing I need to add here is that every time I run this analysis, I want to make sure to reset my counter. Because if I don't do that, every time I run the analysis, the counter will just keep counting up to infinity, and it'll keep adding points. We'll have lots of duplicate data, and we'll end up with a massive data set that has the same slices analyzed many, many times, which of course we don't want. So the way I'm going to get around that is there's a couple different ways we could do it. I think I might do it a different way in the patch that I uploaded, but this is maybe a clearer way, which is that I'm going to take this bang that is my analyze button, and I'm going to first send this bang down here, that middle inlet of the counter. If it receives a bang, it'll reset it so that the next time the counter receives a bang here, it'll output a 0. So first do that, and then go ahead and do the analysis. So that'll make sure that my counter starts at 0. Now if I hit bang, hit the analyze button, seems to be good, no errors. Let us see what our data set contains. We can send it a print message. And sure enough, there is our data set called slices that has 2 columns. That makes sense. That's what we want. Looks like a bunch of spectral centroids. Looks like a bunch of loudness measures. And then the identifiers range an identifier from 0 to 22, which would be 23 slices, which is good. We had 23 rows here. And if we look over here, I think we'll see that we have, I'll do a fluid.buff to list at slice points. And then what I really want to do is I just want to check and see the ZL length. So how many slice points are in this list? Which should be, yeah, okay. At source should be slice points. 24 slice points will mean 23 slices, because we'll always have one less slice than we have slice points. Here, I'll do the analysis. Oops. Identifier already in dataset. What a lovely warning. Error. It's red, really, but what a lovely alert for it to tell me, because I ran this before. So I'm actually going to clear the dataset. But one thing that's nice to notice is if I'm using add point as my message to add points to a dataset, it will not let me overwrite. It'll throw this error and say, you're about to overwrite data. I'm not going to let you overwrite data. Here is the error that I'm giving you. If I used set point, which takes the same arguments, and I were to do this instead, set point actually will overwrite data. If there is an identifier already in the data set that it is trying to write into, it will overwrite that data point. If the data point is not in the data set point will just add it to the data set. So it's a useful tool depending on how you're managing your data, which one to use. I actually prefer to use add point because I like that error. If I'm about to make a mistake, it'll let me know. So I can just clear the data set here with the clear message. And then I'll run the analysis again. So now I think I did the analysis. Let's print it and see. Yep, sure enough, there it is. So now I have my 23 slices. The identifiers range from 0 to 22. And it has two columns. We can see one looks like a bunch of spectral centroid values and one looks like a bunch of loudness values. So that's my data set. Now I'm going to plot it into this plotter. This plotter object is called fluid.plotter. The way that we're going to add the data set to our plotter is we're going to call onto the data set, we're going to call a dump message. And what dump does is it's going to output the contents of the data set as a dictionary, and it's a dictionary in both Max and SuperCollider. And in Max, the dump dictionary is going to come out of this outlet here. So if I just see what happens when I click dump, we get the word dump. It is saying, I have done the thing you asked me to do, that is dump. Then it says dictionary. So it's saying this is a dictionary. And then there's this string of characters. So SuperCollider users won't have to worry about this because we handle dictionaries differently in SuperCollider. But here, what Max is doing is it's actually making a dictionary of data. And it's sort of holding onto it behind the scenes. You know, we don't really see it as an object in our patch here. But this string of characters is an identifier that we can use to refer to that dictionary later. And so what we'll need to do is we'll need to pass this dictionary to our plotter, and then our plotter will know where to go get it, look at the data that's in there, and then plot that data. We're going to route off the dump message, and then we're going to connect it right to the plotter. And then if we hit dump, we see nothing. And that's because the plotter is by default showing us a range between 0 and 1 on both axes. And of course, our data is the spectral centroids are up in the many thousands, and all of our loudness values are going to be below 0. So all of our dots are now in this plot, but they're not where our plot is actually looking in the range. There's a few things that we could do to approach this. We could actually change the range of our plotter here so that it would more accurately match the scaling of our data. We could show many thousands of values on the x-axis and change our y range to from 0 down to -100 or something. A more common approach, and the one that we're going to do here, is we're actually going to normalize our data set before we plot it. And what that will do is that will make sure that all of our values in our data set are between 0 and 1. And then when we give it to the plotter, it will be in the appropriate range that the plotter is already set to display. So, and that's what we're going to do for the rest of the times use the plotter as well. It's usually how, at least with FluCoMa, we end up using the plotter. But if you wanted to change the scale and see things in their native ranges, that is something you can do as well. So the way I'm going to do that is I'm going to make a new data set, which is where I'm going to put the normalized information. Fluid.dataset, normed. And then I'm also going to use a fluid.normalize, which will do the normalization for me. As we've already seen, fluid.normalize will take the message fit transform with 2 T's, fit transform. And the 2 arguments are going to be the data set that it should be normalizing, the one it will analyze, find the minimum and maximum value of each column. That's going to be my data set called slices. And then another data set that once it does the normalization, does the transformation of the data, it will write that normalized data into a new data set. That data set is called normed. So I can connect that and actually just leave these 2 guys hanging out here like this and run that process. And then if I print this data set, we can see that all of my values are now normalized. So now this is the data set that I want to dump and give to the plotter. And now we can see there's my data in my fluid plotter. So that's pretty cool. We can see it. Bunch of drum slices. We know our x-axis is going to be this one, which was spectral centroid. So from the low spectral centroids to the high spectral centroids. And the y-axis is loudness. So from the loud sounds up here to the quiet sounds down here, sort of organized like a spectrogram for some intuitive ways of navigating the plot. The next thing I want to do is I want to be able to click and drag around this plot and be able to figure out, like, what is that sound right there? Which drum slice is that, right? I want to know which it is. And ideally, I'd also like to hear that drum slice. So the way that we're going to do that is we'll notice that as I click and drag around, the plot is actually reporting out for me my mouse, my 2-dimensional mouse position, the X and the Y of where I've just clicked. You can see that this is normalized. It's going to go from 0 up to 1 in both dimensions. If we were to change the range of the plotter, the X range and the Y range, the mouse would actually report out the values in that scaled range. So if our x-axis was from 0 to 20,000, then our mouse would be reporting out here values between 0 and 20,000. But because we're leaving the plotter in this normalized range, it's going to report out these normalized values. In order to find which these dots are, what I want to do is I want to take my mouse position, and wherever I am on the plot, I want to find what is the nearest point to my mouse. There's a tool, an algorithm, that'll let us do this really efficiently. And that data structure is called a KD tree. So I'm going to make an object here, fluid.kdtree. And what a KD tree does is it analyzes the data set. We're going to fit the KD tree to our data set normed, because that's the one that we're actually mousing around inside of, is the data set normed in that normalized space. So the KD tree is going to learn from the data set normed. It's going to organize all of that data in a particular way so that if I want to give it a point and find from the point I give it, what is the nearest point in the data set normed, it organizes the data in such a way that makes that lookup really efficient, really fast, right? We could check every point in the data set and just check every point, find the distance, and then say, okay, well, this one was the closest. For our small data set here, that would probably be fine. Our computer could handle it just fine. But if we start to get into the many thousands of data points, we don't want our computer to have to check every data point to see which is the nearest. The KD tree will make that algorithm, make that lookup for us more efficient and much more fast. So this is why we're going to use the KD tree. So I will tell the KD tree to fit to the data set normed. There, that is done now. Send that message in. And then what I'm going to do is I'm going to ask it for the K nearest. And K nearest is going to be a message I'm going to send to the KD tree. And K nearest needs an argument that is going to be the name of a buffer that has the data point in it that I'm asking, what is the nearest point in my data set to this data point? And because that data point is going to be my mouse position, I'm going to make a buffer in a second called mouse. So I better make that buffer here. I'll call it buffer mouse. And because I know that that is always only going to ever have two values in it, the mouse X and mouse Y, I can just put in here @SAMS2. A little bit verbose to be clear about what my data is here. And then, in order to get my XY values here into my buffer called mouse, so now I'm going to click here on the plot. We'll check my buffer called mouse, and sure enough, it looks like I have some XY values in there. So that's great. So now, I can take this output of fluid list to buff as soon as it is done writing into the buffer. It will output some information for me, which I can sort of turn into a bang very easily here, because then I want to bang this message and tell KD tree, hey, there's a new mouse position in that buffer called mouse, and I want you to find the nearest point to it. And so then I can catch the output of KD tree here, and we'll see what it does. And sure enough, it says K nearest. That is the thing you asked me to do, and so I'm telling you I've done it. And that is 0.12, and this one is 0.1, and this one is 0.0, 7, 16, 13, etc. That's pretty good. And if I move around, if I click and drag, you can see that as soon as I change between two nearer points, it'll change which one it's reporting. Okay. So now we're basically there. I have this, and as we saw before, I can actually tell this little patcher here which sound slice I want to play just by giving it the index of that sound slice as it appears in the slices, and it'll play that slice for me. So I just need to get this 14, put it in here, and we'll get that sound slice playing. The way that I'm going to get this 14 out of here is I'm going to first route off the K nearest part. So I'll do a route K nearest. And then I also need to do a from symbol. And that's because this 14, it is in quotes. And the reason why it's in quotes is because it's actually not an integer. It's a different data type. It is a symbol. And so we can just convert that symbol to an integer using from symbol, and then we'll get our integer that we can pass into our play slice by index function here. Here's my integer. Okay. So now, if I turn on the audio, we can hear those drum hits. And so what we should hope to see here is something where we have the lower spectral centroid sounds over here, higher spectral centroid sounds over here, which seems to check out, and then the quieter sounds down here. and the louder sounds up here, which seems to also check out. So that looks like a successful plot that we might now be able to use in some sort of performance or analysis of our sound corpus, or some other sort of creative way. So one more thing that's kind of nice is our plotter here has a message we can pass to it called highlight, which will show us in the plot where a certain identifier is in the data set. And so if once we find our nearest point with this KD tree and we know what the identifier is for it, if I just pass the highlight message into the plotter, it'll show me by making that plot a little bit, by making that point a little bit bigger, where it is. So this is a nice feature just to really sort of give some visual feedback on what it is that we're analyzing, or what it is that we're hearing.